Hello everyone, my name is Libo Chen. Today I will present our paper, sharing more and checking less, leveraging common imported keywords to detect bugs in embedded systems. Yanhao, Wang, and I are co-leading authors. We finished this work by collaborating with other researchers from Shanghai Jiao University, Jiaqi Technology Research Institute, Penn State University, Tsinghua University, and Shandong University. The Internet of Things has been much more widespread in recent years. It is believed that 5.8 billion IoT endpoints are in use in 2020. We can find so many IoT devices in our lives. However, it was reported that 57% of IoT devices are vulnerable to medium or high severity attacks. There are a large number of IoT devices, and the lack of security in most IoT devices brings more vulnerability. And meanwhile, many IoT devices are connected to the network. So it makes bugs more devastating and often brings significant security risk. In particular, wireless router and web cameras suffer more attacks because they are usually connected to the internet and have weaknesses at many board surfaces. So how to detect vulnerability in such IoT devices? There are many existing methods, including dynamical solution and static methods. Fuzzing is a popular one, but if we want to apply fuzzing on IoT devices, we must have real equipment or run firmware and emulator. Due to different environment and peripherals, it is unscalable to apply emulation for different devices. And meanwhile, specific path conditions is also a common program for fuzzing. Then for static methods like symbolic execution, it is heavyweight in most cases and usually falls into path explosion when exploiting complicated functions. Now we propose another solution. A static method check user input between front end and back end for vulnerability discovery effectively and efficiently. As shown in this figure, on the left-hand side, the front end of router is a JavaScript file. And the back end is a binary named HTTPD on the right-hand side, which calls many functions to handle user input from the front end and have a weak functions labeled with this blue rectangle. I will present more details in this sample. Let's move on. This is our motivation sample demonstrating a real-world vulnerability in routers. There are 4 steps to trigger this bug. First, a user inserts a USB flash device into this router. Then she can check it in the web interface and clicks a mode button on the response page. Then this event is sent to the backend, and a command injection bug happens. Now I will reveal the root cause of this bug. This figure focuses on the details about how to utilize the web interface and the variable code inside this router. On the left-hand side, a user just needed to click a mode button of web interface. Then the front end will send a request with the device name attached. We should see this variable in the line 6 of this JavaScript file, named the device name. On the right-hand side, the backend web server is a binary named HTTPD. And it will pass the request and invoke a series of functions. And finally, it calls a function named form set USB unload to identify the emotion the device name. Synthesize a command string, then execute the command to alter this specify the devices, as shown in the line 4. Unfortunately, we can see there are no sanitization tracking, so there is a command injection bug. An attacker can append extra commands to device name in the front end, available named CMD, that may be embedded malicious commands. For small attacks can directly send a malicious request via link like this and exploit this router remotely. At the same time, we found an interesting phenomenon that a common string named device name repeatedly appears in the front end and back ends. As shown in this figure, a blue dash connects this common string. So our intuition is that the strings shown in the web interface are commonly used in both front end files and back end functions, like this string device name shown in this sample. In the front end, the user input is labeled with a character string. In the backend, the same string is used to actual the use input from the packager. So our novel method is identifying these shared strings and discovering vulnerability from the reference points of these strings in the backend. As shown in this figure, we can connect the front end with the backend by shared keywords, and identify the input processing function in the backend. If this method works, it will alleviate unnecessary path exploring in Taint analysis. As shown in our motivated sample, the Taint analysis prefer to start at the form set USB and root function rather than other Taint source functions like a socket data or input find handle. Obviously, these functions are more directly to use input than others. In other words, it can more effectively catch Taint source entry in these border boundaries. So we need to verify our intuition on normal IoT devices. We inspect 10 routers from the 5 windows to check whether the front end and the back end use common keywords to represent the user input. As listed in this table, on average, 92.4% of the keyword value pairs captured in the front end match those in the back end. So it shows that our intuition works for these common devices. Now we still have 3 challenges for applying our method. The first one is to identify keywords in the front end. And the second one is locating the input handle in the back end. And the third one is tracking the massive passes of user input to detect the vulnerability. To solve these challenges, we design our approach strategy in architecture as shown in this figure, including 3 major modules: input keywords extraction, input engine recognition, and input sensitive data flow analysis. So let's move on to see the details of the strategy. The first module is input keyword extraction. This module extracts keywords from different front-end files, including HTML, JavaScript, and XML files that are embedded in different services. For example, we use regular expressions to extract keywords from the label names of an XML nodes. Then we filter these keywords by several rulers, like removing strings with specific characters such we think these keywords are not related to user input variable. Then we filter out short character strings when they are less than 3. And we remove the character strings in the shared libraries. And we also filter common strings like button, console, and so on. These keywords are usually referenced by many front-end files, but they are not related with user input. At last, we perform string matching between the string filter result and the strings of all back-end binary. Then we simply identify both binary by treating the binary with the maxed matched keywords as the border binary. The second module is input engine recognition. This module not only detects the location inside the border binary that reference to the shared keyword, and also find the input engine in the backend that don't have corresponding keywords in the backend by using a heuristic method leveraging the context in this location. Additionally, we can find the co-process engine by locating the data flow of user input interrupted at the process boundary, such as environment variables, as shown in this figure. And the last module is input sensitive Taint analysis. We conduct a coarse-grained Taint engine that marks the Taint source based on the result of the former module. A Taint source can be a return value or a parameters of target functions. And shown in this figure, the return value named CMD in this red square should be considered as a Taint source that point the user input. And shown on the right-hand side, this is our Taint specification algorithm. We perform instruction level Taint analysis and divide all functions into 3 classes. This method achieved a trade-off between efficiency and efficacy. For evaluation of strategy, we meet these 3 questions. For the first question, can strategy find the real-world vulnerability? We selected these IoT vendors that provide their firmware online, such as Netgear, Agenda, TotalLink, D-Link, and so on. we collected 39 firmware samples from the 14 series as a data set, including routers and cameras. As shown in this table, CLC found 33 unknown bugs, and most of them have been assigned bug IDs. As that at HTTP protocol, CLC also supports other services such as UPnP and HNAP. For the second question, can CLC accurately detect the imported keywords? This result shows that CLC can accurately detect all three types of front-end files. This table shows the number of imported keywords selected by each step of CLC. We should see that in most devices, like less 10 routers, less than 10% of all strings from the front-end files are finally used to catch the imported keywords. And as shown in the columns on the right-hand side, CLC makes the sensitive true positives in the parameter keywords. For the third question, how efficiently and accurate is our Taint analysis? First, this figure lists the number of keywords in each sample detected by our three different modules. We can see that most of the imported keywords are collected by the keywords referenced locator, especially for Taint devices. NetGeo samples contain more keywords located by the Implicit engine finder, and the D-Link samples contain more keywords from the process engine finder. Additionally, for all samples of this data sorter, CLC raised 101 alerts, and 46 of them are true positives. We analyzed those false positives, like this overturned problems occurred because of missing objectors for some common functions, such as A to I function. To summarize, we proposed another approach to detect the security vulnerability in embedded systems. This work is based on the insight that the variable names are commonly shared between the front-end file and the back-end functions. CLC has successful discovery 33 zero-day software bugs, and most of them have been assigned bug IDs. And our code and the data set will be public at GitHub. Thanks for your attention. I'm happy to take any questions.